Okay, before I forget, I wanted to mention that everything I'm discussing during this week, there is a good text about this, which is a book written by Bertrand Hénard called Counting Surfaces. So you can find all the material I present during this week and much more. So there are more examples and connection with other example coming from combinatorics and the relation with random matrix theory. So what I'm presenting during this week correspond to a few chapters of this book. Okay, so let's recall what we did yesterday. We're starting from the problem of enumerating maps. Now, what we did is that we did define some generating series for maps of genus G with n boundaries, where x1 to xn are variables which are dual to the length of the boundaries, which means that if you want to extract information about genus G maps with n boundaries of respective lengths L1 to Ln, you just compute residues of this function times a product of powers of x. Now, a priori, this is a generating function, so it doesn't have any nice analytical property in terms of the x's. But the first thing we did was to study the simple guy, which is the genus 0 with one boundary generating series, and we found out that it is solution to an algebraic equation where E of xy is equal to y squared minus phi prime of x y plus some polynomial p01 of x, where phi prime of x is related to the data of our enumerative prime by being defined in this way: sum over I equals 3 to d minus to d ti x to the power I minus 1. So that's a degree d minus 1 polynomial, and ti, the coefficient of this polynomial, are the weights that I associate to unmarked faces on my maps. Now, the first good information about that is that it seems that I could get a closed formula for this generating series, W01 of x, just by solving this equation. And as I was saying yesterday, if you solve this equation, you've got two branches of solution, depending on the size on the sign of the square root you consider. And we know by definition that W01 of x should behave like t over x when x is large. So it selects one of the solution, which is the one with the minus sign. Now, the question is, how can I compute this polynomial? So I'm saying that I get a closed formula for W01 of x, provided that I know this polynomial. The good thing is that a priori, W01 of x was a generating series, so it's the data of an infinite set of numbers. By having this equation, I restrict this infinite set of data to just the knowledge of the coefficient of this polynomial. So it's just a finite set of number I have to fix, which is equal to the number of coefficient of this polynomial. Now, what I will tell you now is how to compute this polynomial.
Really,
So there are, yeah, so this is, if you want, it's a power series. Yeah. So it's a formal series in T. Yeah, say, I think it's C. It's a formal series in T whose coefficients are polynomial in X and T3 to TD. But the good thing is that in X, the degree of the polynomial, so of each of the coefficients, is bounded by d minus 1. So yeah, but a priori the definition is there. So now what I could do is that it's a polynomial in X. But from the definition, you get it in this way. Yeah. 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 So the point is that. So. Sorry. What is over X?
You justify the choice of minus sign.
Yeah.
Over X. But I don't see it. That's when X is very large.
Yeah, it's when it's very large. So I'm looking at the behavior when X is very large. So if you look at the two branches, one behaves like V prime of X when X is very large. And the other one behaves like something else. And you can find out that with this good polynomial. So yeah, a priori, I don't know that it will behave like T over X. But this will be a constraint which will allow me to compute this polynomial. What I know for sure is that if I take the plus sign here, I will not have the right solution. Because the degree of my polynomial, P01, is too small compared to V prime squared. So it cannot compensate for the behavior. Yeah, so we know the degree. So remember that P01. So let's remind what it is. It was obtained in this way. You take V prime of X times W01 of X. And you take the polynomial part when X is large. So the degree is at most the degree of V prime minus 1. Yeah. So degree of P01 of X is at most D minus 2. Yeah, and that's an important point, to know that we've got this bound on the degree. So D minus 1 is the degree of V prime. And so we've got the D minus 2. Now, indeed, when I'm saying that we know that the right solution is the one with the minus sign, I mean that we know that the one with the plus sign is not a good solution. And know the fact that the one with the minus sign should behave like T over X when X is large will impose constraint on P01 of X. And basically, this is where the information I need in order to fix P01 of X comes from. No. In some cases, yes. In some other, no, from you, no, because it's not right in general. It doesn't have a random matrix representation in general. Because the point is that in order to go from a good random matrix integral to a generating series of maps, you've got to consider some formal perturbative expansion, which doesn't make sense in a general setup. So as a formal matrix integral, yeah, if you want. So you just take trace of 1 over x minus m, and you take the genus 0 part, meaning you look at the large n limit of 1 over n. Yeah, where the measure is that you take the integral over Hermitian matrices of size hn exponential minus n over t trace of p of n. And so you compute the expectation value of this guy. No, I don't want to enter this side because I want to rely only on combinatorics where everything is properly defined. For those who are interested, this is well explained in the book of Enna. And the idea is that there is a connection between this random matrix and this W01 of x and this enumerative map by saying that I can look at a saddle point expansion of this random matrix integral. You write it as, so you make an expansion, you invert the sum that you get from your expansion and your matrix integral. You get a series whose coefficients are given by Gaussian expectation values, so a matrix integral with just a m squared term here. And this can be represented as a generating series of fat graphs, so graphs where your vertices have a cyclic orientation, and fat graphs are dual to maps. No, this path of writing a perturbative expansion is not rigorous in general. That's why I don't want to go there, and I don't need it for our purpose. But yeah, for people who like random matrix integral, you can keep that in mind. OK. So let's go back to this problem. So what I know for sure is that W01 of x is solution to this equation. But you see, actually, when I write W01 of x, if I'm just thinking of a solution to this equation, I need some additional information to tell me what is W01 of x. It's not a function only of x, but it's a function of x and a sign. Meaning that if I look at the complex plane, take an arbitrary value of x, if I want to know which branch of solution I have, so let's say that I start from W01 of x, which is defined with the minus sign. Question, can I analytically continue this solution in the whole complex plane? So by definition, what I did was to say, I've got a point which is infinity, and I define W01 of x as a series in 1 over x, which is well defined around infinity. And I want to extend it in the complex plane. What I found out is that it's not that bad. A priori, it could be just a series in x, which is non-convergent, which doesn't have any nice analytical property in x. But what I find out is that it's actually something which is analytic, but has a square root. And so if I would write this just as a product, I just look at the zeros of this polynomial here, x minus ai, I equals 1, so I can look at the degree. The degree is d minus 1 times 2. So A1, A2, A3, A4, A5, A6. I cannot analytically continue my function W01 of x on the whole plane, but if I just draw branch cuts emanating from the zeros of this polynomial, then I can analytically continue this function on the complex plane minus the branch cuts. So just think of the usual case where, the simplest case where I would have just square root of x. I want to define this function in the complex plane. Got 0. I cannot, but what I can do is take a branch cut going from 0 to minus infinity and say that I define my function square root of x, let's say, with a plus sign here. And I can analytically continue it on the whole plane minus a branch cut. And what I could do is say, OK, actually, I could define a multi-valued function on the whole plane by saying that whenever I go across this branch cut, I change the sign of my square root. So if I've got square root of x here, then on the other side, I will have minus square root of x. So here it's the same. I've got a function which I define around infinity. I want to define it in the whole complex plane. The only obstruction I have is this square root. which is square root of a polynomial with a priori 2d minus 2 zeros. So I can continue it in the complex plane minus a set of cuts emanating from these zeros. And saying, OK, I can define it, this W01 of x, as a function on the complex plane minus s cut, or as a function on the complex plane, which is multivalued in the sense that whenever I make an analytic continuation and I go across a cut, I will change the sign in front of this square root. So that's one way of doing things. But another way is to think of it as saying that if I look at this x-plane, I think actually I have two copies of them. And I say, OK, I start from choosing a branch of solution. Let's say the one which corresponds to W01 of x. So when I'm sitting here on this point, x, then the function W01 of x is equal to v prime of x minus square root of v prime of x squared minus 4 p01 of x divided by 2. Anyway, I will say that in all this plane, this is true. So the value of this function on this plane minus s cut is equal to that. But now what I will say is that whenever I cross such a branch cut, I don't stay here, but I go to another copy of the x-plane with still infinity, such that if I look at the point x here, the value of W01 of x is equal to v prime of x plus square root. So I change the sign. Yeah. 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 I decompose the product here. Yeah. Yeah, the whole expression. So what I want to know are the zeros of the polynomial which is under the square root. So now, what I did here is to say, I started from some W01 of x, which actually is a bad notation because it's a multivalued function of x. And I want to have a function of a variable which will be monovalued. So what I do is that I replace my complex plane by two copies of the complex plane, which are linked by branch cuts, such that I don't have this ambiguity anymore. Now I've got two copies of the x-plane, and the two copies they represent the two branches of solution of my equation. And if I think of it as a surface, then when I'm sitting on any point on this surface, it is parameterized by what? It's parameterized by the value of x, so the point where I am. But it's parameterized also by just a parameter saying whether I've got the plus or minus sign, so saying on which copy of the x-plane I'm sitting. And you can parameterize it by saying that this new object, which I will call a surface, is equal to the set of x and y in C2, such that E of xy is equal to 0. Now, how do I characterize a point in this surface? I characterize it, for example, by the value of x together with a choice of branch of solution here, which correspond to choosing a copy of the x-plane here. Now, if you think of it in this way, it means that this can be thought of as a surface which is a double cover of C of the X-plane, meaning the following thing. If I take a point X in the X-plane, I look at all points in my surface sigma such that the first coordinate is equal to X. I've got 2 points of this type corresponding to the 2 solutions here, and they correspond to 2 points in my surface here. Okay? So is it clear? This is really unwavering geometry. Yeah. So no. So these are function of, so for example, this guy is a polynomial in X. So let's look at what is here. This is a polynomial in X, and this is as well, with coefficients which are just the t's. So yeah. Yeah, so I will fix a value. Yeah. So I fix a value. I fix a generic value actually of the TIs. Yeah. No. If you look at it as a Power series in T, it's not actually. It is not. Yeah, you've got a finite reducible convergency. So this you have to show. Indeed, it's hidden under the cap, but you're right. Yeah, such that this is well defined. Yeah. So if you want, you will have a family. So here, if I would have some good notation, I should have some T and T here. This equation depends on a small t and capital T. And you've got a family of such curves. And generically, a priori, it looks this way, because you've got as many zeros as the degree of your polynomial here. Yeah, so actually all the information that you need is encoded here. So the T are hidden in the V prime in a very simple way, but they are hidden in the AIs. And that's exactly what we will try to find out. Can we have an expression of the AIs in terms of the T's? Yeah. Now, P01 is defined in this way. So you take V prime times W01 of X. So, and you take the polynomial part. This is a polynomial of degree d minus 1. This behaves like 1 over X. So the product behaves when X is large as d minus 2. So the degree of P01 is at most d minus 2. And the degree of V prime is 2d minus 2. So it's larger. Okay? So that's the first thing which is very important, that we've got control on this polynomial here. Yep. So that's what I will look at. So this would be a priori. So here I just look at what would be a generic case. I would have just simple zeros. Now we will find out that in this case, this is not true. And we're in a much easier position, which is that apart from 2 zeros, all of them are double zeros. And this will make the picture much nicer. So now, just think of it in this way. So from this point of view, what I did is that I replaced my algebraic equation by a surface given as a surface in C2 defined by this equation. So the set of points in C2 which satisfies this equation. And I can think of it as 2 copies of the complex plane which are linked by cuts. So they are glued together. Now, actually, what I want to think of is to add here infinity such that I compactify everything. So I think of the X-plane as a sphere, where I just add the infinity points. And so the surface is now 2 copies of the sphere which are glued by these cuts. So the picture is basically the following one. You've got a surface sigma, which a priori looks like that. You've got 2 copies of the sphere, which are glued along some bridge cuts. So the genus is generically equal to the number of cuts minus 1, which will be, so here remember that I've got d minus 1 cut. So the genus of sigma is a priori, so is at most equal to the maximum number of cuts I can have, which is d minus 2. Okay? No. So let's go back here. No. So, no. So the number of cuts is d minus 1. Yeah. So the number of cuts is d minus 1, and so I've got a d minus u. Yeah. Just a small remark. You see that d minus 2 actually is the maximal degree of my polynomial. And in some sense, there is some interplay between the degree of my polynomial and the genus I've got here. In this very specific case, what we will find out is that there is a very nice lemma saying that actually the genus of sigma is equal to 0. And that's what I will describe now. And this will make life much easier if you want to do computations. So this is called Broad's lemma. Maybe before I go there, is there any other question about this picture of replacing my algebraic equation by a surface which is a double cover of the explained? No? Because I will use that a lot later on. This will be the fundamental object for the following. What we shall say is that basically all the information about the problem I'm trying to solve, this problem of enumerative geometry, is encoded in the geometry of this surface sigma. So as I was saying, for W01, you see that all the information of W01 was encoded in this polynomial here. And so I translate it into the definition of a Riemann surface. And what will be beautiful in this work is that actually the information about all the WGNs for arbitrary G and N are also encoded in the same surface. Yeah? So here I'm not talking about moduli spaces. So you think of the hyperelliptic locus. Yeah. So here I will just study, in this talk, I will just study the generic case. Now, what is interesting later on is to go to some singular points in this space. And this is related to the question you can ask, which is, I wanted to enumerate maps, discrete surfaces. Some people do that in order to know what would happen in a kind of continuous limit where you take the number of faces to infinity and you look from far away so that it looks like just having a continuous surface. This kind of behavior is obtained when you look at singular points in this moduli space. But I will not look at them. So I will look at the generic case. Yeah. 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 This will be the classical limit, the large n limit of this curve. Yeah. Because you see you should be able to recognize it from there, I guess. No. I mean, the point is that you see the equation I did write on this Tutte equation and the form in terms of generating series. These are what you would call loop equation. These are the same whether you come from the formal world or the convergent world. No, the question is that actually what I did write down would be some 1 over n square expansion of the equations that you have from your conversion side. The point is that this expansion does not exist in general. It exists only in the formal case or in some very specific cases in the random matrix world. Yeah. So these are very particular cases. Here I'm just working with t's which are complex numbers small enough such that my series are convergent and I can define it. So I don't have any other stuff. Yeah. Okay. Now, what is Brown's lemma? Remember that I had this square root which was basically looking at v prime of x squared minus 4 p01 of x. So the ai's which are there are roots of this polynomial. Brown's lemma says that this actually can be written as m of x squared times x minus a plus x minus a minus. Meaning that in this setup, if I come from an equation E of xy, where p0, 1 of x comes from this prime of enumerating maps, if I look at all the zeros, except for 2 of them, all of them collapse and are just zeros, double zeros of my polynomial. Yeah?
This suggests some way to number the groups.
What do you mean? Yeah? Well, I mean, I do not make any connection between the zeros and the labeling here. Yeah, because I will tell you what they are. Such that a plus minus is equal to alpha plus or minus to gamma, where alpha is, sorry, T3 to TD. It's a series in capital T, and gamma square as well.
That's the same about the which square root is gamma?
What do you mean, which square root? Ah, yeah. Yeah, okay.
So there's no way in general the polynomial doesn't have a root.
So I just choose one branch for my gamma. I just pick one. In the T-space, you mean? Yeah, but I will fix the value of the T's. As we were saying, I just take a very particular value of the T's, fix it for now, which is small enough such that, so I fix it. When I do that, then I choose a root here. Yeah. Yeah, I mean, yeah, but related to a question, actually it's related to your previous question, which is that no, here I'm interested in what happens when I fix the t's and I move in the x. But then you can ask the question, what would happen if I would move in the t space, so this parameter space? If I think of it from this curve point of view, I can have some degenerate cases. And when I go around, I could have monodromies, which would exchange my roads and so on. But so here I fix the t's, and I choose just one particular branch of this. And such that alpha is of order t, and gamma square is equal to t plus some lower order term. And m of x is again a formal Power series in T. Yeah, I mean, I could take the same notation. It's a polynomial in X with coefficients which are formal Power series in T, and polynomials in the small t's. Yeah, I think that's it. And we know that m of x is equal to v prime of x over x plus some higher order term in T. So, yeah. What? That's what I'm saying, yeah. I'm saying that if I want to enumerate maps, then whatever happens, the spectral curve you consider, this surface sigma, has only one cut. So it is known from people like you, like the one-cut assumption. It is not an assumption. It is not an assumption here. I started from some problem of combinatorics. And this combinatorial problem imposes that I have just one cut. It imposes that. Now, you could define some other combinatorial problem which correspond to enumerating some kind of nodal maps. If you do that, then you can have more cuts. But if you just want to enumerate maps of this type, the type I defined here, then it fixes for you the fact that you just have one cut. It is not an assumption. Yeah, but it's not a random matrix. Yeah. No, but yeah. Yeah, but so I am not talking about random matrix integral. Here I'm just doing combinatorics. That's all. I know it's confusing to people, but that's why I don't want to talk about random matrix integral. Because as soon as you do that, then you have to make sense of this perturbative expansion. Then if you're not careful enough, you will have to make some assumptions. For example, the assumptions that you will have a one-cut curve and so on. But you've got to say what it is here. And it's something which is really hard to prove, and in general, it's not true. So here, it's completely different. I've got a well-defined problem of combinatorics. I define some generating series W01 of x. It's solution to an equation, which is fixed. And by definition, because I started from this problem of enumerating maps, this equation defines a curve where I just have one cut, just one. So I will sketch the proof very briefly. It's a bit technical, but the idea is the following one. All of these are Power series in T, capital T. And what you do is that you look at what happens order by order in T. So you start from the T equals 0 case. And you look at the leading order of this equation when T is equal to 0. What you can find is that if you look at P, so this doesn't depend on capital T, but P01 of x does. And remember that this was defined as the positive part, so the polynomial part of this. But W01 of x behaves like T over x when T goes to 0. So it means that P01 of x is equal to T P prime of x divided by x plus some order terms. Now if I look at this equation, so if I look at this polynomial and I look at its leading part in T, so take the T equals 0 limits, P01 of x doesn't contribute. So a priori, this is the square of a polynomial already. So you just have double. So if you write v prime of x as a product from I equals 1 to d minus 1 of x minus capital Xi. In the t goes to 0 limit, this is just equal to v prime of x squared. So I just have double. Now, what you can do is study what happens when you look just at the leading order in T. you see that you're just switching on one term, which is v prime of x over x in this equation. And so what you're doing is that before you had your roots of v prime, which were double zeros for this polynomial, x1, x2, to x d minus 1. And just by looking at this leading order in T, since you will, you want to look at leading order when T goes to 0, here you will have to take the square. You want to see this as the square of a polynomial. So what you find out is that your original double zeros will be divided into pairs of zeros, where the distance from the original root to the new ones is of order square root of t. So you can make it more precise, but that's the idea. You start from something which is a polynomial independent of t, take its square, and you perturb it by something which is of order t. You want to write it as the square of a polynomial, and you find out that this polynomial has roots which are the original one, but actually they are. What? Because you want to write it as product of x minus I going from 1 to 2d minus 2. So I started from something which is square of a polynomial, square of this one. So here I'm just looking at that. You see, I mean, my statement is just about this. No, I didn't say anything different. So I just said I start from this v prime of x, which is what happened, the value of this polynomial if t is equal to 0. And now I look at the t expansion of this polynomial. What I'm saying is that to leading order, in t I will get another polynomial whose roots are the double root that I would get from there, but shifted by some square root of t on both sides. So I double it, and the distance is of order square root of t. And this is the idea behind the behavior of this gamma here. Now, a priori, I still have a lot of cuts here. But now what you can find out is the following thing. The first thing to remember is that v prime of x, I will keep on doing it here. So v prime of x, remember it was x minus sum over j equals 3 to d tj x to the power j minus 1. So actually, we know one of the xi's. One is equal to 0, because you can factor x. I will do it for you. X to the power j minus 2. So there is a particular root, let's say the first one, which is at 0. Now, if you look carefully at the T expansion of all the ingredients you've got here, what you can find out is that actually these are just double roots. And one, yeah, so it's not, the idea behind that is that if you look at W01 of x, which is a Poirot series in T, you look at it order by order in T, what you can find out is that if you compute the integral of W01 of x along some contour here, this will be vanishing unless 0 is inside this contour. And this you get it by doing some study of the T expansion of this function. So if you want, these are filling fraction, but here there are no filling fraction because there is only one contribution. The other one are by that. Yeah, so it's giving you T if 0 is inside C and 0 otherwise. So this follows from the study of the T expansion of W01 of X. Because if you look at W01 of X, it's a formal Power series in T, but the coefficients are polynomial in X. And so you can really perform this kind of integration. Oh yeah, these are polynomial in inverse powers of X. So if you look at the coefficient of T to the power of V, it will be a polynomial of fixed degree of 1 over X. So it has poles only when X goes to 0 or infinity. And so it prevents you from having branch cuts or from having singularities anywhere away from 0. So it means that these cuts here do not exist. Yeah, I mean, it's a bit sketchy. That's why I just wanted to give the idea of the proof. The idea is that we've got formal Power series in T, and we know the behavior of the coefficient of this formal Power series in T. And this imposes for you that you've got this form of Fourier polynomial. Yeah. Yeah. Yeah, that's what you need. Yeah, you need, I mean, there are some convergence theorem in terms of T, which I didn't want to present here. No. Yeah, so, okay. Yeah. Yeah. Yeah, okay. So one way to think about it is to think of it as a relation in the space of Power series in T. And so you just think of it as coming from the coefficient of your Power series. And that's exactly what I would do. I just look at the coefficient of my Power series, formal Power series, and I get an infinite number of equations which are all satisfied. No, the convergence. The combinatorics? Yeah, no, what I'm using as well is that the coefficient of T to the power of V, remember, is a polynomial of bounded degree. Yeah, and that's what I'm using. But this comes, from my point of view, this comes from combinatorics in the sense that, yeah. No, yeah, right, yeah. No. Yeah, but it's a condition on the coefficient of T to the power of V, on the polynomials that you can have here. So you could restate that in terms of constraints that you can have on the coefficient of T to the power of V. I mean, when you say the number of maps with fixed number of vertices grows in a way, you can restate that in terms of knowing something about the polynomial. But yeah, I mean, from my point of view, this comes from the fact that I start from this specific problem of combinatorics. Okay. No. We've got this nice relation here, which means that actually my W01 of X reads V prime of X over 2 plus or minus 1/2 m of X, square root of X minus A plus X minus A minus. And this picture is much nicer now, because before I had a genus G curve, but now I've got two copies. Of the complex plane, of the Riemann sphere, which are glued together just by one cut. So it has the topology of a genus 0 surface, or topology of a sphere. And this will make the computation much nicer, and I will tell you how to use that in the following. So I think I will have a break now. Maybe there can be some questions. What? I don't remember. Okay. Okay. And since we're there, maybe now you can mention the origin of the generalization to Tutte's equation. What you told me yesterday about the fact that Tutte's equation, the area genus generalization, was found by. Okay. Yeah. Thank you. Okay, so let's have a break. Okay, so if some of you are convinced by this lemma, the important point is that at the end of the day, I've got such an expression for W01 of x. So it's a good polynomial in x, another polynomial in x times a square root. And I just have two roots for the polynomial, which is below the square root. And my claim is that the surface sigma, which I defined earlier, which is the set of xy in the sphere such that this algebraic equation is satisfied can be represented as two copies of the sphere which are glued by a cut. And this gives me a genus zero surface, which topologically is just a sphere. So maybe I should make the picture a bit more clear by doing that. Just take the sphere. I've got my a minus a plus. The same on the other side, a minus a plus. So on the x-plane, a minus a plus. And I used to draw the cut in this way. But actually, you see that you've got two sides for this cut. So you can cross it from one side or the other side. So one way to think about it is to think of it as small slit in this way. So you can enter from this side, and then you will get out on the other copy, but from the other side, and so on. And if I do that here, it's like saying that I've got a small tube which links my two copies of the sphere. Now, the good thing is that in this case, when I've got such a solution, or an equation which defines a curve which is a double cover, so two copies of the sphere linked by a cut of this type, there is a natural map. We'll remove that, which will give me some good coordinates on this sphere. So you see that up to now, I write everything as function of x. But that's not a good idea, because W01 of x, which is the important object, is not a monovalued function of x. It's a multivalued function of x. What I want is to promote it to a monovalued function on this sphere. So in order to do that, I would write it W01 of a variable, which is a coordinate on this surface. Now, I would like to find a good coordinate. And since I was very lucky to have this Born's lemma, here I can do it. You see that when I make this picture, you could think of it in this way. So you've got two copies of the sphere. So you've got 2 points where x is equal to infinity. One of them is the one where W01 of x behaves like t over x, so it's the good one. So let's call S plus this copy of the sphere, and S minus the copy where, if I would like to be consistent, it should be S minus and S plus. So S minus is the copy where I've got a minus sign for my W01 of x. So it means that on this copy of the sphere, when I go around x equals infinity, this behaves like T over X, which is the good solution I'm looking for. While on this copy, this behaves like V prime of X when I go to X equal infinity. And what I will do is say, OK, I'm sitting in S minus, and I'm looking at, from this point of view, I'm looking at S plus as being inside this small slit. So I will open it up. So if I'm sitting there, and I start thinking of this picture a bit more carefully, I open this slit. So I've got my point X is equal to infinity, and I've got my copy S minus, which is where I've got my minus sign. What I did say is that actually this other copy is obtained just by, I go there just by crossing this cut. So I've got two sides. Can go from there or there. And crossing this cut just takes me to the copy S plus. So actually here, I've got another copy of the sphere minus the cut, which is the copy S plus. So now, if I've got this picture, I've got just one copy of the sphere with a circle, which goes through my two branch points, which represent my cut. And now I could say, OK, I've got the sphere, so I could have a global coordinate. Let's call it Z. And I will be more precise. I will use some transformation, which takes me from this representation to the one where this is the unit circle, and A plus and A minus are taken to +1 and -1 respectively. And that's what is called going to, we'll try to Zukowski's variable. So the idea is that you want to go from this picture, which was S minus A minus A plus, where this is actually a cut and S plus inside, to some reference picture, reference genus 0 surface, where you've got a cut, which is the unit circle, such that the roots here, which is what I will call branch points, sits on 1 and -1. And here I will have some Z coordinates, such that S minus correspond to Z, which have modulus bigger than 1, and S plus are the one which have modulus smaller than 1. And this is very explicit, just obtained by just writing x of z as a function of this coordinate as a minus plus a plus over 2 plus a plus minus a minus over 4 times z plus 1 over z. So remember, for a fixed value of x, I have 1 point on each copy of the sphere, 1 point in S plus, 1 point in S minus. What does it mean from this point of view? It means that if I fix x for a fixed value of x, actually I've got 2 points, 2 values of z, which give me the same result. And these 2 values of z, they are related. They are just z and 1 over z. So here we can see that we've got a symmetry, which is the exchange of z and 1 over z, meaning that if I'm standing here at a point z, I've got another point 1 over z. The value of x at this point and this point is the same. And this is exactly the kind of identification I want to have, such that I've got this double cover picture. Now, if you do that and use this variable, what is interesting to me is the following object. So remember that here, this is a well-defined function of x, just involves polynomial, except for the square root. Now I want to go to this z variable, which lives on this double cover, in such a way that I can define a well-defined monovalued function on this plane. So I had some function of x, so with this transformation, it's OK. The only missing part is just the expression of my square root in terms of these z variables. And now the first observation one may have is that x I want it to be invariant under the involution which exchange z and 1 over z, because I want it to not know on which copy of the plane I'm sitting, so whether I'm in S plus or S minus, whereas the square root, I want it to change sign when I go from one to the other. So it should be something which should be anti-symmetric when I exchange them. So it should behave it should behave like z minus 1 over z. And you can find the coefficient, it's just a plus minus a minus over 4. Such that, indeed, it has zeros. So this polynomial, we know that it vanishes when x is equal to a plus or x is equal to a minus, which correspond to z is equal to plus or minus 1. And this indeed vanishes when z is equal to plus or minus 1. OK? So now, I've got this expression. So I just found some nice coordinates, these Zukowski coordinates, such that I can express x and the square root just in terms of this coordinate. So from this point of view, if I replace x here by x of z and the square root by what I did right down here, I can write it as a function of z, which is monovalued in z. And I recover, so there will be 2 points corresponding to x going to infinity. One is z goes to infinity. The other one is z goes to 0. And the point is that the meaningful information I want is what happened when I've got x goes to infinity in the s minus side, which correspond to z goes to infinity here. So when I want to do my residue computation for getting numbers from there, I will just compute residue when z goes to infinity. And I will do that explicitly later so that you can see it. No, it's not over. Here I've got a nice parametrization of my problem, but I still don't know what a plus, a minus, and this polynomial m are. So let's look for them. OK, so first question. Can I write v prime of x of z in these coordinates? So the first thing is that we know it's a polynomial in x. So it should be invariant under the extension of z and 1 over z. And in addition, we know that it is a polynomial of degree d minus 1. So actually, we can write it as a combination of this type, where k goes from 0 to d minus 1. Yeah. So what was the constraint? So one way to find it is to say, OK, I write it as a polynomial in x. X can be written in this way. But what I want to do is to actually rewrite it as a polynomial of degree d in a basis which is invariant under the exchange of z and 1 over z. It's a polynomial in x. So x is symmetric when you change z to 1 over z. So remember, z goes to 1 over z. It exchanges the 2 copy, so it changes the sign of the square root here, but it doesn't change x. So it changes the sign of the square root, and that's all. Since it doesn't know anything about the square root, it needs to be symmetric. OK, so that's the first part. And now remember that we've got W01 of x of z, which now I will abusively, maybe I can put a twiddle. So I call W01 of x of z as W twiddle of z. So now I started from what would have been a multi-valued function of x, but I've got a good coordinate z such that I can have a mono-valued function. This is a bad notation because this is a well-defined function. And the point is that if I just write down the equations there, so it's equal to v prime, v prime of x of z over 2. And I will write it as minus, so I use the minus convention for the sign, minus some function of z, which is basically this 1/2 m of x square root of x minus a plus x minus m minus. Okay, let's write it in this way, where y of z is equal to minus 1/2 m of x of z square root of x of z minus a plus x of z minus a minus. And now this function y should be skew-symmetric when you exchange z and 1 over z. So it's the other way around. Basically, here I've got a decomposition of my W01 into a symmetric and some skew-symmetric parts. And so if you look at the degree of this polynomial in z, if you look at the behavior of this function of z, you can see that it will take a very similar shape. Where now you've got a basis which changes sign when I exchange z and minus 1. Sorry? No, because I will use it. But yeah, u0 will be equal to 0. What? No, but I will need, yeah. It's a parameter, but this parameter will be fixed by the equations. What do you mean? So it's a, yeah, sorry. Yeah, in this case, yeah, okay. Yeah, okay. No, sorry, yeah. No, I thought you were talking about the one above as well. Okay. Now, we've got this decomposition of this W twiddle of 0, 1 of z into this symmetric and anti-symmetric part. But, yeah, what you know is that when z goes to infinity, which is this point here, corresponding to x goes to infinity in the S minus plane, these behave like t over x of z plus your order in t, and actually you just have negative powers of x which appear. Okay? This means that actually this can be written down as sum over a priori L going from 0 to infinity. Let's call it tk c to the power minus k. So, yeah, thank you. Beta k. Sorry? Yeah. Or at least k. Yeah. Now, if you write down just these two equations, just this equation using this representation, what you find out is that it means that the positive part coming from y and v prime should compensate. So the positive part of the z case here. So this imposes that u twiddle k is equal to minus uk. And it also imposes that here you just have a few of the beta k's. This is just the sum over k equals 0 to infinity uk z to the power minus k. So you just take these two expressions, this one and this one. Thank you. So you take this expression and this one. Their sum should be W twiddle. So you've got one part which is the positive part. You know that you just have negative part. So they have to compensate. They vanish. So it fixes the value of the U twiddle k. But in addition, this gives me the value of my beta k here. Yeah, it's just a notation. So one of them is a function of x, the other one is a function of z. Ah, no, yeah, they are equal, yeah. Yeah, it's just. Yeah, there is a factor 2 if you want to go from this one to this one. So identify the UK to the U twiddle. Yeah. Yeah, should put a 2 here. Should be okay now, right?
No, it's still not right.
So I've got, no, that's okay. So I've got V prime, which is, so I've got UK plus U twiddle K. So I've got the twice here. Sorry? No, yeah. Yeah, but it's just in the definition of the the U twiddle. I didn't write that it was equal to UK. Yeah. Okay. So now I just did restate my theorem of finding this M and this A plus and A minus, or finding this W01. I once again turned it into another theorem, which is finding these UKs here. Now, the UKs, I define them here. But V prime is a polynomial in X. So now, actually, I've got a nice way to find the UKs. So, yeah. First thing, if you look at this representation on this part, what you find out is that U0 needs to be vanishing because of this behavior here. And U1 needs to be equal to 4t over A plus minus, A plus minus A minus. So you know that W twiddle 01 of z should behave in this way. X of z is defined by this equation. And I look at it when z is large. So it doesn't contribute, so it behaves like A plus minus A minus times z over 4. I put it back in this. It gives me the leading order of the expansion in z to the power minus k. So just the leading order is 1 over z. So it gives me that C0, U0 is equal to 0. And in addition, it gives me that U1 is a fixed number depending on t, A plus, and A minus. No, not here. The little t dependence is hidden there. And now it will appear in the following. So these are just two constraints. So a priori, I want to fix d minus, d UKs, and I've got two equations. It's not enough. That's what I'm going to do. Yeah, but so that's what we can do now. Is that you substitute x of z inside this equation. Z plus 1 over z. And you write it under this form. So you start from there. You've got a polynomial with coefficient dependent t. Write the expansion in terms of the z and one over z variable. Write it under this form. It gives you some UK, some equation which relates the UK and the T3 TD capital T. So it gives you a set of equations, as many as you've got for UKs. But this equation involves A plus and A minus. Yeah, you get expression for the UK in terms of this.
Just expand
Yeah.
V prime
Yeah.
and
Exactly. Yeah. Yeah. So I mean, you've got a closed expression. I don't want to write it down here. You can make the math. It's very easy. You just have combinatorial factors. So you get this expression. But now you've got only two unknowns which are left, A plus and N minus, A minus. And we're lucky. We've got two equations here. Now you write down the equation, U0 of T3, TD, T, A plus, A minus equals 0, and the same for U1.
so you're getting two ways to write.
So this will give me the A's. So I've got two equations with two unknowns. And what you can show is that there is a unique solution which has the good property in the capital T expansion, so the behavior in terms of T. So we will do an exercise. We'll make an exercise to see how it goes in some specific cases. For A plus and A minus, there will be two solutions, which will be. So if you want to have this kind of expression, alpha plus and minus 2 gamma, where alpha is of order t, and gamma square is t plus order t square. There is a unique solution provided that you choose. So there are two solutions if you want. And this corresponds to the exchange of A plus and A minus here. Yeah, but you think of it as a equation for formal Power series in T. And there is a unique solution up to a change of sign here. But yeah, a priori, if you don't have this kind of structure, you would have some higher order polynomial. Here, I know that W twiddle 01 of Z, when Z goes to infinity, I know that it's a series in 1 over X of Z. So it just has negative powers of Z, which appear. Because it's so one way of saying that is that I know that this is regular when Z goes to infinity. So it doesn't have any positive part in Z. Yeah, but that's OK. What time is it? OK. So maybe let's summarize what we did here. Once again, we want to enumerate map. We want to compute this generating series. And first, I just look at the simplest case, which is W01 of X. Out of that, by Tutte's equation, I can define an associated algebraic curve. And I find out that it's a curve of genus 0. Because of this very nice property, I can use some global coordinates on it. And if I write down all the properties that I know for this W01 as a function of Z as a formal Power series in T, then it gives me some constraints which allow me to reduce everything to a set of two equations which encodes the position of this branch point, A plus and M minus. And I can solve it. Let's say there is a unique solution to this equation. So now I could trace backwards and re-express. No, what I want to compute is this A plus minus. It's the same as knowing alpha and gamma. You can write down this equation in terms of alpha and gamma as well. So either you write it as equation for A plus and A minus, or as equation for alpha and gamma. They will be fixed by this equation. You've got two equations, two unknowns. And as formal Power series in T with this property, there is a unique solution. Yeah. So it means that now we found out a way to find this A plus and A minus. So to find the UKs, and when I know the UKs, I know W01 as a function of Z. And that's exactly what I was looking for. Now, the last thing I wanted to do is that out of W01 of X, I wanted to extract some numbers by computing residues. And this I can do. I just take W01 twiddle of Z. And I know that the meaningful information is encoded when Z goes to infinity, which corresponds to the right point at infinity for X, the point where this behaves well, like T over X. And I just take this, compute residue of W01 of Z, the X of Z, X to the power, X of Z to the power L. Residue when Z goes to infinity with a minus sign. This will be equal to what I called T0L in the previous lecture, which is a weighted sum over genus 0 surfaces with one marked face whose degree is equal to L. I've got a closed expression for that, provided that I know the UKs, which I just compute by this. I know X of Z, so I can compute the X of Z. I know X of Z, I can take its L's power, so I can compute this residue. It gives me these numbers, which are series in T with coefficient, which are polynomial in small t's. Okay? So I guess that for people doing combinatorics, it's a maybe strange way of doing things. Looking at generating series is often a very good way of looking at things, but even more, here we're very lucky by knowing that the generating series we defined actually can be promoted to a monovalued function on an associated Riemann surface. And because we've got this Riemann surface, we can do some complex analysis on it, compute some residue, and as soon as we know what surface we're dealing with, we can compute this kind of numbers. And this will be the scheme which will be followed in all the lectures, which is that whenever you have an enumerative problem, you want to associate to it a Riemann surface, and you will work on this Riemann surface because it will encode all the information about your problem. So let's make an example. We look at quadrangulations. So what I mean there is that Tk is just equal to T4. So I take D equals 4, and I take T3 equals to 0. It means that I will enumerate maps whose faces are just squares. So the unmarked faces are only squares. OK. Now, if you follow this scheme, so the first thing to notice is that you've got this sum from k equals 0 to 3, uk, z to the power k plus z to the power minus k. No, I will write down explicitly in this case these equations. So you get U0 is equal to alpha times 1 minus T4 alpha 2 plus 6 gamma square. Yeah. So I use this transformation here. So you can work, yeah, I mean, you can write down your equation as an equation in terms of A plus and A minus or alpha and gamma. U1 is gamma minus T4 times 3 alpha squared gamma plus 3 gamma cube. And the remaining ones are easy to write down. It's minus 3 T4 alpha gamma squared. U3 is equal to minus T4 gamma cube. Not that bad. So remember that what I will compute here will be a generating series for quadrangulation of disk of whose boundary as arbitrary lengths. So there is a lot of things I can compute with it. I mean, a lot of numbers. But here I just have some simple equation and not many of them. The expression of the UKs in terms of alpha and gamma. And now I just write down this equation. So U0 is equal to 0. So what solution do I have? U0 is factorized. So you could have a solution which is alpha equals 0, or T4 alpha squared plus 6 gamma squared is equal to 1. Remember that alpha and gamma are a priori formal Borel series in T. And I've got this constraint, which is that alpha is of order T and gamma squared behave like T. So when T goes to 0, alpha and gamma should vanish. So this cannot vanish, because you would have 1 is equal to something which goes to 0 when T goes to 0. So the first equation implies that alpha is equal to 0. No, the second equation then gives you, so you write alpha plus minus alpha minus is equal to 4 gamma. So it's T over gamma. So here the equation is 4T over alpha A plus minus A minus. A plus and A minus are alpha plus or minus 2 gamma. So the difference is just 4 gamma. So replace it here. I've got 4T divided by 4 gamma. And I've got just this equation, which is that T is equal to gamma 2 minus 3 T4 gamma 4. So it gives me an equation for gamma 2. So gamma squared is 1 over 64 times 1 minus square root of 1 minus 12 T4. And I guess people who work on combinatorics of quadrangulation know this square root, or recognize it. So I found my alpha and gamma. Now I can find my UKs. And it gives me a very nice expression for W01, which is T over gamma Z minus T4 gamma cube 1 over Z cube, where gamma is given by this equation. Sorry? Yeah. Thank you. Okay. No. Yep. Sorry? Yeah. Yeah. So that's what I will find out So now what I want to do is to compute some residue here. Yeah, you mean this square root, yeah. Might be. Here, over there? Yeah, here, it's a large T. Yeah, thank you. So now, final step is to compute this T0L, which is the minus the residue when z goes to 0, and I write it down again, W01 of z twiddle x of z to the power L dx of z. So, first thing you can see is that here I don't have even, yeah. First thing you can see is that here I just have even powers of z, and it implies that T0 to L plus 1 is equal to 0 for any L. So you can make the computation, and you will see that indeed you've got this property. It comes, you can see it coming from the symmetries there. And this is completely natural, because here we're enumerating quadrangulation of a disk. And this imposes that the boundary of my quadrangulation needs to have an even number of sides. So it means that the number of such maps which have an odd number of sides has to be vanishing. Now, what about T0 to L? The expression is this one. It's gamma to the power 2L. 2L factorial divided by L factorial, L plus 2 factorial, 2L plus 2 times T minus L gamma square. So I've got a closed expression for T0 to L in terms of gamma, where gamma is just written under this form. If I would have liked to compute that by enumerating maps, saying sorting them by the number of vertices they had, I would have to look at the T goes to 0 expansion and compute all the terms. So it would give me an infinite series. And the point is that this infinite series can be recast under this form, where gamma square is given by this equation. So this is, I find, a pretty nice expression for these numbers. And you see that the way I went there was, again, start from my combinatorial problem, associate a Riemann surface, define my generating series as a well-defined function, monovalued function on this Riemann surface. And then in order to recover the information I was looking for, I just compute residues. Yeah. So I think it's a good place to stop. Now what I will tell you what I will do next week. So here, you could say, OK, that was quite a lot of work in order to find the g equals 0 and equal 1 case. Question, what would happen for higher genus and n? Do I have to do exactly the same thing? So what I will do is write down exactly the same kind of equation, Tutte's equation for arbitrary g and n. There will be some unknown, which will be some polynomial. And now you can wonder, OK, do I have to find a Riemann surface associated to each different g and n? And the magic here is that, no, you don't have to. All these WGN for arbitrary g and n, you will be able to promote them to monovalued function on the same Riemann surface. So actually, this hard work of finding the Riemann surface associated to W01 of x, I have to do it just once. And what I mean by that is that actually there is, to this whole problem, there is only one Riemann surface which is associated to it, which encodes the combinatorics I started from. And then there will be a universal procedure to associate to this Riemann surface a set of WGN, which can be computed by induction. And that's exactly what we call topological recursion. So next week, I will present it in this setup of enumerating map. And if I have time, I will start developing the general setup. But the idea will always be the same. Start from some enumerative prime, associate a Riemann surface just by looking at the generating series of disks. And once you've got that, you just run your recursion. Okay, so I think I will stop here.